last time to take a shot at coding a basic analysis for regression. So let's begin there. So the first thing, obviously, that you need to do is you need to read in your CSV file. Just do all of that. So once you have your CSV file in, you've got relative humidity and you've got weight loss. These are the two variables that are in the example in the PowerPoint. And so the first thing that you'll want to do is build a model for this. Somebody other than Chance, because I think if I recall correctly, Chance answered every question last time, so he's on mute for today. Somebody give me a shot at what the syntax for the model should be. Okay. What's that? Okay. Okay, so let's do that. And it didn't give us any errors, so what do we need to do next? Okay. So we could just type in model, and it gives us some stuff. It will give us it'll basically give us the equation for the line. So it gives us the y-intercept, and it gives us the slope value, so that we know that weight loss equals 8.704, what is it, 03 or 93? Helps if I don't put my cursor over the thing I'm looking at. Minus 0.0533, nope, 322 times relative humidity. So if you just ask it for the model, this gives you the equation for the line, but it doesn't tell you whether that line has a slope that's significantly different from zero. It doesn't really tell you anything else about the about what the statistical model is giving you. So Logan suggests do summary model, and this gives us a lot more information. This tells us not only what the coefficients are, but it also gives us the p-values for whether the intercept is different from an intercept of zero and whether the relative humidity is a slope value different from zero. And we see that the slope has a p-value associated with it of 7.82 times 10 to the minus 7th, which is a highly significant p-value. It also gives you other things. It gives you things like the r-square value. In this case, 0.9745. It gives us the F statistic, gives us the degrees of freedom, and this is basically what this p-value is based on. So this p-value here should be the same as this p-value here. So this actually gives you the statistical test. Yes, this is a significant negative correlation between these two variables. But normally we would be able to calculate R square ourselves. We can calculate R square. What is the equation for R square? Do you guys remember? Samuel's looking it up. Yep, that is exactly what it is. Do we find sums of squares anywhere in this output? We do not. So try summary.AOV for that model. And what you will see when you do that is by tacking on the .AOV, it actually gives you an analysis of variance table. Looks very much like the analysis of variance table that you get when you run an ANOVA. It has the degrees of freedom for each of the sources of variation, the sums of squares, the mean square, the F, and the P. Once again, all of this should match what is up here because you're running it all on the same model. But what this does is it gives you the sums of squares. The sums of squares due to regression is 23.514, and the sums of squares total is 23.514 plus whatever the residual value is, 0.616. 24.130. 24.130. And if you do this, it should give you that. And what that basically is telling you is that most of the variation in the y variable, in this case, most of the variation in weight loss is due to this model that relates weight loss to relative humidity. Once you've accounted for relative humidity, there's hardly any residual variation left over, such that the statistical model, this is the model, the model is accounting for 97%, over 97% of the variation in weight loss. So I was talking to Hayden yesterday, and one of the challenges that you have when you're doing data analysis is figuring out ways to basically interpret the data for people who might be receiving the data, figuring out how to express what the data mean. Because when you analyze data for somebody, you can't just like throw them back in a ANOVA table and say, here you go, there it is, have fun with that. And so it's important that you become comfortable and fluent with, okay, so now I've run a regression, what does all the output from the regression mean? Not just for me and my statistical brain, but for the person receiving the data. So interpreting what an R square value is in a way that has meaning for people is important. So this is why you see me repeatedly describing what R square means, because that's important. But ultimately, it all relates back to things that you're already familiar with, things like the calculations of sums of squares. So that's the model. And this will be valid assuming that what kinds of things hold true in terms of the assumptions underlying the model. What are the assumptions of a regression that are necessary for this model to be valid? I'll get you started. The first thing is these are groups of beetles that were all weighed as a group. So presumably one of the things that needs to hold true is each of those groups of beetles needs to be independent of one another. So these are flower beetles. Have you guys ever seen flower beetles in a flower at home? You have some old flower and you look inside and there are little beetles inside there. So you have your canister of flour sitting in your cabinet at home, and you come home and you see that it's full of beetles. Now, to do this study, you had to take the beetles and put them in different conditions of relative humidity. Well, inside this single canister of flour, because you've been a negligent baker, you go in and you grab out nine beetles and you transfer them to another container that's smaller because you only have 9 beetles. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 beetles in it, and you put this at 0% humidity. Then you go and grab 9 other beetles and you put them in another canister. Put this at 12.5% humidity, etc., etc., etc. Are these independent? Why would you say that they're independent? Okay, so they're independent because they're in their own canister. But they kind of have to be in their own canister because you're setting the relative humidity, right? This is a sealed up jar that's been sitting in your cupboard all this time. It may have been that at one time, when you got this from the store, there was a single female beetle in there. She laid a bunch of eggs. Some of these eggs were males, some of these eggs were females. And then those siblings all got together and mated with one another. And each of these females produced a bunch of eggs. Some of those were male, some of those were female, etc., 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 until you go into your cupboard one day and your flour is full of beetles, and then you're like, oh, I have a population of beetles. I can do something interesting with them, or something not very interesting with them, depending on how you view this particular project. Then you take them out of here and put them in their own individual canisters that are subject to a particular relative humidity. Are these different canisters at different relative humidities? Are they independent of one another? It's a no, because they all came from the same place in this case. They are all the descendants of one female. They're all the great, 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 great grandchildren of that first female that was trapped in that canister at the very beginning of all of this. And so even though you've split them off into individual containers, they're not independent because they're potentially all related by familial relationships because they've been stuck in that main canister over a long period of time. So the first assumption is that the data that you're gathering are independent. And there are a variety of ways in which your data can be non-independent of one another. This just happens to be one of them in a biological sense. We could measure anything about you guys here at William Jewell College. We could, for example, look at the correlation between your SAT scores and your final GPA. Are those data independent of one another? In one sense, they could be, because each of you is an individual, such that your SAT score has nothing to do with your SAT score, and your GPAs don't necessarily have anything to do with one another. But in what way are they not independent? They're all pulled from a single population, but pulling them from a single population isn't what makes them non-independent. How did we make up this population of you, students at William Jewell College? It wasn't convenient. You've had to apply. You've had to have a certain SAT score. There was a screening process. You went through a series of hoops. Some people were denied entry because they didn't have adequate scores or adequate grades in high school, et cetera, et cetera. Some people were denied because they couldn't afford to pay the tuition here. So in that way, because you've all gone through a common selection process, there is a certain degree to which you guys are not independent of one another. You are all the outcome of a common selection process. And so one could argue that you're not independent because of that way, because of that process, especially because the thing that we're looking at is your SAT scores and your grades. If we had an open enrollment policy such that your SAT scores didn't enter into the admission decision criterion, then you would be more independent than you currently are. But because SAT scores figured into whether or not you were admitted, then using SAT scores as a predictor of GPA in a regression makes you somewhat non-independent because we don't have a random sampling of students with a lot of different random SAT scores. We have a population of students, all of whom had to cross some threshold to get into the place. And so thinking about independence is sometimes tricky, but it's something that you should get familiar with. But that's the first of these assumptions, is the assumption that the data that you have in your sample are independent of one another. What are the other assumptions? Yes, that they are randomly sampled. If I looked at your GPAs and your grades for students in this class as my sample, that's not really a random sample, that's a sample of convenience. That is only informative if I'm interested in what this relationship is between GPA and SAT scores for data science students. And therefore, I can't extrapolate that to the entire campus because you guys are a non-random subset of the population that I might be interested in extrapolating to. So they're randomly sampled. These two things, when do you deal with these two issues, these two assumptions? Yeah, these are all taken care of when you're collecting the data, when you're designing your study, whatever your study happens to be. You don't get to the data analysis section, portion of a project, and be like, oh shit, my data are not independent. You needed to fix that before you collected any data. If you come to a statistician and he or she looks at your data and finds that they're not independent, you're basically just kind of up a creek at that point without much to paddle with. So what are the things that you have to deal with after you get your data? Yep, and what's the last one? So we can do some assumption checking with these data. Let's start with the easiest one, which is checking residuals. How are we going to do that? Somebody give me a possibility. Okay, so I'm going to just call this res. So okay, so we get to keep using a model over and over and over again because we specified our model up earlier. So that gave us a line of code that didn't throw us an error. Before we run this code, before we look at the output of this code, what should we expect it to look like? Should have some positives, some negatives, should be kind of equally weighted, positive and negative, in terms of their magnitude and the number of them. And how big should that file be? There should be 9 values. Okay, so when we run that, so when we type in res here, we should have 9 values. Some of them are positive, some of them are negative, and they should all sum to 0. And it's negative 1.18 times 10 to the minus 17th. That's basically just rounding error. So you can always check residuals because residuals should always sum to 0, or in this case, something amazingly close to 0. And they do, which is good. So now that we have a file full of residuals, what do we need to do? Yeah.
But mine is not the same as yours.
Oh,
So,
what is mine?
Yours is there.
Okay.
So I guess I must have messed up on one inputting.
Let's see. Oh, let's go look at the data file. I'll call them out. You check them. 12, 29.5, 43, 53, 62.5, 75.5, 85, 93. Okay. 8.98, 8.14.
8.98. Okay.
That's the reason. Yeah. But let's check all of them.
Okay.
8.98. There you go. 8.14, 6.67, 6.08, 5.9, 5.83, 4.68, 4.2, 3.72.
Thank you.
Sure. Yeah.
How do we know that we're going to be 9 residuals?
Because you have 9 values. You have 9 pairs. Yep. So that comes from the original data set. If you get some number of residuals that is different from your total sample size, something's gone haywire somewhere. So whenever you run a line of code, you should use your own knowledge of how that process works, how that method works, such that you should be able to predict certain things about what the output from the line of script you just wrote will be. So when you run residuals, you should expect 9 residual values if you have 9 values in your original data set. For the P's analysis, you had 5 different treatments. Each treatment had 10 values. If you got 60 residual values out of that, then something has gone wrong someplace. So always be thinking, I try to always think whenever I write a line of code, okay, here's a line of code. What do I expect to see out of that? Because that's one of the ways in which you can check errors in R. Simply because R doesn't throw you an error code doesn't mean that you didn't screw something up. It just means that it was capable of doing the thing that you asked it to do. You may be asking it to do some batshit crazy thing in the terms of getting the analysis done, and it'll do it if it's capable of doing it, but it may give you something that is totally wrong and useless. So always be thinking to yourself, I just asked it to give me this. What do I think that's going to look like? And then if it doesn't look like that, then go back and check stuff. So that's a good habit to get into. And this is also why students are like, why do you make us work these things out by hand? Well, because by working them out by hand, you kind of get a feel for what you can expect. Because I constantly get, well, actually I haven't gotten this at all from you, but in past semesters, I'm like, talking to students, they're like, why do we have to work these out by hand when we're just going to do them on a computer anyway? Well, because you can get the computer to give you almost anything. And with R, it's a little harder because you have to know how to ask it to do certain things. But if you get out of here and you go to a place and they run like Minitab or Statistica or something like this, where there's a menu of things and you just click on buttons to specify your model and get output and stuff, like you can do all kinds of damage not knowing what you're supposed to be doing in those packages because everything is automated and run in the background and you're just clicking buttons on things. And so it's a lot easier to get astray there. But once again, even in those programs, if you kind of know what you're expecting to see when you ask that program, even though it's a menu-driven program rather than a scripting level program, if you know what you should be expecting to see, you will be able to know whether or not you've asked it to give you the things that you want it to give you in the right way. So yeah, be predictive about it. All right, so everybody have residuals? All right, how do we test residuals for normality? Okay, Shapiro test, and we're going to test that on the residuals. And once again, when we do this, um, it doesn't give you sample sizes or anything else, so there's not a lot of diagnostics that you can run on this. You assume that things are running okay because you've done checks before this. You've checked that your residual file is 9 values long. You've checked that it sums to something resembling 0. And then what we find here is that these residuals are normally distributed. Is there a way of looking at these? To give us a sense as to whether we should believe this test or not? Okay, so we can do a histogram. But with only 9 values, it's not going to look like much because it's only 9 values. What else can we do? How else have we looked at normality graphically in the past? Chance, it looks like you're dying. QQ norm and QQ line, right? If I'm recalling correct. Nope, not QQ line. Something I don't do that often, so I forget what the exact code is. What it was it? Oh, I put 3 Qs. Oh, that's my mistake. Heavy fingers. Oh yeah, there it is. So even though we have a non-significant normality test, why do we have a non-significant normality test? So, but if we have outliers at the top and the bottom, if we have these outliers here and these outliers here, that would tend to make us think that these data are not normal because normal data should all lie along the line, right? Why, if we have 4 out of our 9 values lie pretty far away from the expected line, why do we still get a p-value of 0.6015? Yeah.
Is the question, why do we get non-significant?
Why do we get a non-significant when it looks from the plot like there's some stuff jacked up with our normality? You have outliers at the top end and outliers at the bottom end. Why do we have data that when you do a QQ plot of it looks not normal, yet when we test it with the Shapiro-Wilk test, we find that it doesn't differ from normality? Why do you fail to find any difference when you think there is a difference there in many cases? in order to see deviations from normality, or in order to see differences among treatments in an experiment, in order to see a significant correlation, what do you have to have enough of in order to look at those differences? You don't have enough data to test these data adequately for normality. So you could have data that differ pretty widely from normality, and you just don't have the power to see it because you only have 9 data points for the test. And so the data would have to be pretty far outside of normality in order for you to detect it. So once again, as we get further into the semester, I want you guys to become more nuanced in how you view your results. So if this is your question, are the residuals around the line normally distributed? You go and look for that answer using the Shapiro-Wilk test. The Shapiro-Wilk test can give you one of 3 answers. Yes, they are normally distributed. No, they are not. What's the third answer? I wouldn't say maybe. You don't have the statistical power to tell. People who look at their data in a non-nuanced fashion will see and be like, check, they're normal. Woo, let's move on. Because they won't interrogate that number any further than that. They won't build a histogram for it. They won't do a QQ plot. A QQ plot that looks at it and says, oh, almost half of your data lies significantly away from the expected line. What's up with that? Well, I get a non-significant Shapiro-Wilk test, not because the data are probably normally distributed around the line. I'm getting a non-significant Shapiro-Wilk test because I don't have enough data, I don't have a big enough data size to adequately test normality. So be careful with how you treat these things. It's fine to say, okay, I don't have any evidence to say that it's not normal, but this is also not a great deal of evidence to say that it is normal. It doesn't mean that you can't proceed. It just means you need to be aware of that. Especially with this data set, when we look at the graph, we see that the graph actually conforms pretty well to the linear model. What makes these outliers stand out is that all of the data kind of in the middle of the regression are all really close to the line. And so it makes any data points that are far away from the line, even if they're only far away from the line relative to the other points, it makes them stand out as big outliers. So I'm not going to worry about this too much, but it is something to think about. But this should also, as you think ahead, this should also point out some potential problems with the next thing that we have to do. So let me go back here. Early on, I made graphs of these data. Yeah, the graph doesn't look so bad. All right, never mind. So what's the next thing that we have to do? So it looks like, so we haven't been annotating this thing, or I haven't been. So we need to generate residuals. Then we need to test the normality of these. Then after we test normality, we're going to look at the results. So that we can actually see for our own eyes if we believe what the Shapiro-Wilk test is telling us. So what's the other thing that we need to test in terms of assumption checking? We've done this. Yes, that is how we would do it in an ANOVA. Unfortunately, a Levine's test is just an analysis of variance on the deviations from the means. And so we can't actually do that here because there are no treatments that we're comparing means. But within R, there is a thing called a non-constant variance test. And you can run a non-constant variance test by basically using the following code that I did not expect you guys to find, because you probably weren't even aware of this test. But the syntax for it is NCV, capital TEST, and then whatever your model is. Oh my gosh, I got an error. When I see this type of error, what does this mean? I didn't load whatever package this thing exists in. Anytime R says it can't find something, if it's telling you that about your data, it means that you haven't loaded in your data yet. If it tells you about some test you're asking, it means that you haven't loaded the package that contains that package, that command in it. Have we loaded any packages yet? No. Why did we not load packages? We've had them loaded in the past, and we didn't know that we were going to need a new package. So how do we know where the non-constant velocity test is located? Well, that's assuming that there's a package called NCV test, but it's probably just a routine within a package. But we know that it's NCV test, so we can go to the help menu and type in NCV test, and we find that it's in package car. So let's pause here and load a couple of packages. So we know that we're going to need car. What other packages might be useful to us as we continue through here? We might need ggplot. What else might we need? We might need RMISC, we might not, but RMISC just has a bunch of stuff thrown into it, and so it's always just kind of a good idea to have RMISC on hand. So let's start with those. And now let's run our non-constant variance test. And what we find is that it's a chi-square based test. And once again, basically we find that we don't have a significant difference, a significant variance in the data as we go across the X values. So we can then get a visualization of this. I didn't check this before I came to class today, and I probably should have. Spread level plot basically shows us what our fitted values are and what our expected values are. So this is a plot of what our expected values are, expected values and fitted values are. And essentially, once again, we're looking to see if this varies significantly, if this increases or decreases much over the process of this, over the scope of this. What we see is it's increasing, but there's a lot of variation around this line such that that increase isn't really significant. And so what you would hope to see in this line is you would hope to see a flat line. And when you do see a sloped line, you would hope that the data are really messy around the line such that the confidence intervals around that line are really big. And so this is just a visual way of looking at the outcome of this test. So the other thing you should see is around this line, the distances shouldn't be particularly large in one part of the plot and small in another part of the plot. So it looks like we satisfy, to a certain degree, the normality assumption and the variances assumption. So the things that we might want to do now is make a graph. So how are we going to start off making a graph? Okay, so we'll start with ggplot. What's the first thing we have to give a ggplot? Not aesthetics. Yeah, so we need to give it the data frame. Then we give it aesthetics. And for this type of plot, what are the aesthetics we need to give it? In a regression plot, what are the primary things that we have? And this way, the aesthetics are not that different from the aesthetics in an ANOVA. You have an X and a Y, yep. All of these plots are Y plotted versus X. So in this case, what is X? You can always go back and remind yourself of what the data frame looks like. Okay, so X will be relative humidity. Don't forget the period in there if you had a period. And what will the Y be? Weight loss. Do we need to add anything else to the aesthetics? Do we need like Y min, Y max, all that stuff? No, because in that case we were looking for within sample variation, within treatment variation. We don't have treatments, we just have an X and a Y, so we don't need any of that stuff. But of course, if we just ran that, it wouldn't give us anything except a frame because we have to add data to the frame now, right? How are we going to add the data points to the frame? And we can just leave it at that for now. Why am I getting an error? So if we run that, the simplest of all possible figures, we get a plot. It looks ugly. It's lacking certain things, but we at least now know at this point that we have the data, and the data look kind of like how we expected them to look. What else do we need to do with this plot. Okay, it might be good to add a line to it. How are we going to add a line? Okay, we can try geom line, but is this any particular line? Let's look and see what happens if we add geom line. That's not really what we want, is it? Not a QQ line, because that's something that we use for theoretical quantiles in a residual plot. We're actually asking it for the fitted line, the best fit line. And so how might we do that? No error bars here. Now remember that whenever you type in something, you can use the features within R. You start off with geom underscore, and then it gives you a bunch of things that you can choose from. So let's just run through the list here. Density plots, error bars, geom function. What is function about? Whoop. Let's go back. So I was at function, right? Function computes and draws a function as a continuous curve. This makes it easy to superimpose a function on top of existing plot. The function is called with a grid of evenly spaced values along the x-axis, and the results are drawn by default with a line. So this looks like it would draw a fitted line, right? So let's put that in our storage banks and see if there are other options. What does geom smooth do? Aids the eye in seeing patterns in the presence of overplotting. Geom smooth and stat smooth are effectively aliases. They both use the same arguments. Use stat smooth if you want to display the results with a non-standard geom. So it seems like geom function or geom smooth, either one could work. Let's start with geom function. It said in geom function that the default is a line. So we'll just try that. Oh no, we didn't give it the function. Okay, so let's try geom smooth. Oh, that's a low S. So this is a low S model. This is a type of regression that basically does smoothing such that it uses local estimates of slope, but we want a global estimate of slope. And so what we need to do here is when we do geom smooth, one of the things that it's going to ask us for is what method we want to use. And in this one, the default is low S. So if we type in method equals low S, I think it has to be this way. It gives us, whoa, it gives us nothing. It gives us the same model that we had before. So let's do, this is, what we're running is actually a linear model. So the method that we will use is a linear model. And now it should give us a straight line.
Do I need it in quotations still?
No, you don't need it in quotation marks. That was me screwing up.
What does all the stuff in red mean?
Remember that in some cases, R gives you error messages to tell that you screwed up. In some cases, it gives you error messages just to inform you of what it's doing. And all it's doing is it's saying, you told me you use a linear model. The linear model that I'm using is whatever your y variable is regressed on whatever your x variable is. So that's all it's telling you. It's an informative error code, not a you mess something up. And you know you didn't mess something up because you got the best fit line out of it. What else did you get out of this? It's a 95% confidence interval. And it's a 95% confidence interval of the slope. So what it's basically saying is that you've estimated the slope, and because the estimate of the slope is an estimate, it has error associated with it in the same way that an estimate of a mean has error associated with it. And what it's basically telling you is that this could be the correct slope of the line, but it could be any slope canted back and forth around the pivot point here at 50.03 or whatever the mean of relative humidity was. If you can pivot a line and keep it within these boundaries, that's a valid slope of that line. If you pivot the line too far though, and the slope no longer fits within that band, then that's a slope that is significantly different from the slope that you're observing. So one of the nice things about this is that, what did I do with my marker? If you have a slope and it has a nice tight confidence interval around that, this slope could be equally valid and this slope could be equally valid. This slope is not. So one of the cool things, one of the reasons I like using error bars when we're doing an ANOVA is because I can look at the error bars and I can look at the means and I can see if this mean fits within this error bar and I can see if this mean fits within this error bar, and I can look at the graph and see intuitively whether or not those means are different. In this case, the hypothesis that you're testing is that the slope equals 0. So if you're here at 50% relative humidity, that basically serves as a fulcrum. You have a line of best fit that goes like this, and then you have a confidence interval around that line. And so if you teeter-totter this line at that fulcrum, it only teeters this far one way, and it only teeters this far the other way, staying within that. If you teeter-totter a slope of 0, and that doesn't fit in the confidence intervals, then your slope is different from a slope of 0. If your confidence interval, on the other hand, you have the same predicted slope, but your confidence intervals are really big because your data are really messy, and they don't do a very good job of X predicting what Y is, you can easily plot a slope of 0 within that confidence interval. And if you see that, when you look at the statistical test of your regression, you should find a non-significant regression because this line is not any different than a slope of 0. Both of those lines fit easily within this confidence interval for the slope of the line. So once again, plotting data in a way that you can see what the error is around your estimate, in this case we're estimating a slope of a line, plotting the confidence interval for the slope is useful to the receiver of the data because you can eyeball that and say, there's no way we can fit. If we take this, there's no way that we can fit a horizontal line inside that confidence interval. And so we have a statistical test that says that that slope is different from a slope of 0, and now we have an intuitive visual representation of that result. I don't know how the college feels about me drawing on their screens, but I don't care. Okay? Now, is this the prettiest graph that we could create? No, it's not. We could pretty this up in all kinds of ways. Among the things that we can begin with is getting rid of the background. It's already cleaner than it was. And here you can specify this. Um, there are other things that you can specify about the way this thing is represented. You can change the size and appearance of the points. You can do all kinds of things. You can change the fonts of the X and Y axis. You can change how the X and Y axis appear. So right now it's just by default giving you the X, Y axis as they appear in your data set. But you can change these to and it would help if you could spell humidity correct. Oops. Don't forget to add pluses at the ends of things. So you can do whatever you want to make this more appealing. Notice that when I add things to the X and Y axis, I will almost always put the units that things are in. So relative humidity is in percentage, weight loss in this case is in milligrams. Whatever information you can put on a figure to help the receiver of the figure interpret that figure to the best of their ability. If you can do that in making better designed X and Y axis labels and things like that, then by all means do so. But basically, you're on your way to creating an informative graph that tells somebody something about the data. Questions about this? We were off a little bit because of Easter, and I think your scripting skills fell off a little bit. Are they coming back to you? Okay, good. That's regression analysis, simple linear regression. We have roughly 10 more minutes left. Any questions about this simple example? All right, for the next 10 minutes, what I want you to do, in your Moodle folders for, I think, last time, there is a data set. The data set is massshootings.csv. So read in that. Obviously, this won't work if you don't have it already in your computer somewhere. I am. I'm just going to make myself a new data frame. Oh, what happened? Oh, that's what happened. I spelled wrong. Shocking. Whoa. So hopefully you've downloaded this. If you haven't, then download it to wherever you store your data files and then read it in. Put your stickies up when you're done. Blue sticky or green sticky up if you've finished, and red sticky if you're having difficulties. we don't have 10 minutes. We have 4 minutes. I don't know why I was saying that. All right, everybody got it done? Yeah, good. Okay. So mass shootings are defined by the FBI as any shooting where there are at least 4 fatalities or more. Last year we had 2 mass shootings in the United States. This year we've had 5 already. And a lot of people notice that one of the consequences of the pandemic is that the rate of mass shootings in the United States fell dramatically, largely because we were all kind of locked away in our homes and not really going anywhere. And so, so over the last couple of weeks, there's been a lot of shootings in the news, if you guys follow the news. And so this got me thinking about, how do we talk about mass shootings? What do people say about mass shootings? And as I was following the coverage of the couple of shootings that we had last week, I thought to myself, when I heard a politician say something that I thought was insanely stupid, I thought to myself, oh, there are data out there that we can use to address the issue. And what the politician said was, something along the lines of this. The United States is an inherently violent society. We were founded in violent revolution, and this is just kind of the way it is, the way it's always been, et cetera, et cetera. And of course, the reason that he's saying this is because he doesn't want Congress to take up gun control legislation, et cetera, et cetera. And so I thought, well, is this actually a true statement? And, have we always been a violent nation? Have we always been subjected to the prevalence of mass shootings that we have today? And so I went around and I went looking for data. And there are a couple of forms of data. The FBI maintains a database. That database has been mined by news organizations. So I used 2 sources of published data. One published by Mother Jones, which is kind of a liberal-leaning publication. But then the other data set that I looked at was Reuters, which is a European news service. The Mother Jones data goes back further. It goes back to 1982. And so 1982, I think to 1990. There's only Mother Jones data, but then from 1990 on, why do I keep saying 1900? 1990 to the present is covered by the Reuters database. And when I got to the point where they overlapped, I started comparing the 2 sets of data, and they match up perfectly. So they're getting their data from the same place. And so I asked this simple question. This question: has this rate of mass shootings actually been constant over time, as this particular politician says, or are they increasing? Because you hear other reports in the news that basically say mass shootings have been on the rise for the last couple of decades. And so this isn't a question of politics, this is a question of data. Either mass shootings are on the rise, or they're on decline, or they've been at a constant rate. So if we take data where year is the x-axis and number of mass shootings is the y-axis, this will either be increasing, it will be decreasing, or it will have a slope of 0. Those are the 3 answers to the question, and you don't need a politician to tell you this. you have the ability to go and find data and test these hypotheses yourself. The hypothesis in this case is that there's a slope of 0, and the other hypotheses are that it's decreasing or increasing. So it's a classic regression problem. So what I did is I went and I found these data starting in 1982, looked at the number of mass shootings per year, looked at the number killed in these mass shootings, looked at the number injured. You can calculate the number of kills per incident. So in a year where you have one mass shooting, it killed 8 people, that number is 8. If you have 2 mass shootings with 28 people killed, that rate is 14. Unfortunately, you have to correct this by population because as you get more people in the country, you might have more mass shootings because you have more people. So I also went and got census data from the U.S. Census Bureau, and then I divided the number of mass shootings divided by population, and then multiplied that times 1,000,000. So this is the rate of mass shootings per million population, and this is the number of killed per million population. And so these numbers are small because you're dividing really small numbers by a really huge population size. But these represent population corrected numbers. So homework for tomorrow, because we don't have class on Friday, because Friday is colloquium day, which you will all be going to see your colleagues and friends and supporting them in their scholarly endeavors. So tomorrow, what I want you to do is I want you to conduct a regression analysis on population corrected numbers for number of mass shootings and the number of people killed in mass shootings, and come to class tomorrow prepared to share your code with one another and to talk about this particular analysis. Questions? All right, comments on the Post-its, and I will see you guys tomorrow. Samuel, I forgot to turn these back to you last time, so I have them out. Yeah. Yeah. Yep. I'll be here. And Hayden, you're coming by also? Yeah, after I get out of class at 10:05. Yep. Yep. Sticky notes. Sticky notes. Give me the sticky notes. Thanks, Logan. Oh, it's increasing. Politicians are idiots.